So in this question, we have a function which is the fraction of hemoglobin F that is bound to oxygen, and that depends on the variable P, which is the concentration of oxygen. The equation that models the relationship between the hemoglobin, fraction of hemoglobin F, and the concentration of oxygen is f of p equals p to the m divided by k to the m plus p to the m. Remember that p, the concentration of oxygen, is the variable, and m and k are positive constants. M and k depend on the species. So these constants are fixed depending on the species. Now suppose m is equal to 2. We're going to prove that the second derivative at the value p equals 0 is greater than 0. So let's start with figuring out what the function looks like when specifically m is equal to 2. So in the general function f of p equals p to the m divided by k to the m plus p to the m, m is the constant 2, so we plug in 2. So we get f of p, the concentration, p, which is the variable, is equal to the variable p squared divided by the constant square plus p squared. Where are we getting the square from? Because we are substituting m is equal to 2 in the original function. Now we find the first derivative, and that is by using the quotient rule. We square the denominator times d by dp, because we are differentiating with respect to the variable p, of p squared minus p squared times d by dp of k squared plus p squared divided by k squared plus p squared the whole square. D by dp of p squared is 2p. We are differentiating p squared with respect to the variable p. D by dp of k squared is 0. D by dp of p squared is 2p. Divided by k squared plus p squared the whole squared. Now we simplify the expression first, so we get 2p times k squared plus p squared minus 2p cubed, and that is divided by k squared plus p squared the whole squared. We factor out 2p. So when we factor out 2p from 2p times k squared plus p squared, we are left with k squared plus p squared. When we factor out 2p from 2p cubed, we are left with p squared. Because 2 and 1 of the p's is gone, we are left with p squared. That is divided by k squared plus p squared the whole squared. Now simplifying, p squared minus p squared, the 2 get cancelled. We get k squared, and 2p times k squared is 2pk squared, the whole divided by k squared plus p squared the whole squared. So f prime of p is given by 2pk squared. This is the simplified form, divided by k squared plus p squared. So now we find the second derivative of this function. Again, it's a quotient. I'm reminding you once again that p is the variable and k is the constant. So, and we are differentiating the function f with respect to p. So we use the quotient rule. So we first square the denominator. So we have k squared plus p squared the whole squared, squaring the denominator. Denominator times derivative of numerator minus numerator times the derivative of the denominator. So now we have k squared plus p squared the whole squared. D by dp of 2pk squared is 2k squared, which is the constant. We leave it alone. dp by dp is 1 minus 2pk squared times, and we're going to differentiate, k squared plus p squared the whole squared. So it's 2k squared plus p squared to the 1, 2 minus 1, that is 1, times d by dp of k squared plus p squared, which is the inner function. So we are using the chain rule. k squared plus p squared the whole squared is to the fourth power in the denominator. K squared plus p squared in the numerator, the whole squared, times 2k squared. After simplifying the first part of the expression. Next, we simplify 2pk squared times 2k squared plus p squared, that's not a whole square. So we get 2pk squared k squared plus p squared times the derivative of k squared plus p squared is 2p. Now we factor out k squared plus p squared to the 1. We can also factor out a 2, and we can also factor out a k squared. So we're looking at these two terms and trying to figure out the common factor. So now, factoring out the given term, we're left with k squared plus p squared. Because it was a k squared plus p squared the whole squared, one of the k squared plus p squareds is factored out, a k squared is factored out, a 2 is factored out, and this is all we are left with. Now in the second expression, the 2 is factored out, the k squared is factored out. So we're left with minus 4p times p, which is 4p squared, times k squared plus p squared. So in the second expression, let me just highlight it in a different color. So we're looking at this second expression. We factor out a 2. So one of the 2's is gone, as I said before. I'm just trying to double check. We have a p times p, which is p squared. We're left with a 4. But remember, the k squared plus p squared is also factored out, so that is gone as well. So now let's see what we have in the denominator. We have a k squared plus p squared whole to the fourth power. And this is equal to 2k squared times k squared plus p squared. And then we have k squared plus p squared minus 4p squared is minus 3p squared divided by k squared plus p squared whole to the fourth power. So we have the first power here and a fourth power here. So we cancel this and that becomes a 3. So we have 2k squared times k squared minus 3p squared divided by k squared plus p squared the whole cubed. So what we have here is the second derivative of the function f. Now we're going to plug in p equals 0 because we are trying to prove that the second derivative at 0 is greater than 0 when p is equal to 2. When p is equal to 0. So we plug in 0, p equals 0. So we have 2k squared times k squared minus 0 because p is 0 divided by k squared plus 0 the whole cubed. Simplifying, we get 2k squared times k squared is k to the fourth power divided by k squared the whole cubed, which is k to the sixth power. So let's think about why this is always greater than 0. Now no matter what k is, it doesn't matter whether it's a positive number or a negative number, k is when it's raised to an even power. Whether this is positive or negative, your answer is always going to be positive. And the same with the denominator. Whether k is positive or negative, when you raise it to the sixth power, it's always going to be positive. So the answer which is the second derivative at 0, is always positive, which is the same as saying that the second derivative when p is 0 is always greater than 0.